this video, we're going to talk about Newton's law of universal gravitation. And we're actually going to do some practice problems with this equation. What I really want you to get out of this lesson is, first off, the value for G, the universal gravitation constant. This is something that you should commit to memory. We have it in data tables, but it's going to be used so often throughout this unit that we should just have it down pat. The other thing I'm going to want you to be able to do is calculate the local field of gravity, or the value of G, for any of the planets, any heavenly body, really. So to do that, we're going to start with this question. First, we're going to ask, what is the weight of a 120 kilogram man on Earth? And then we're going to ask, what is that man's weight when he's 1,000 kilometers above the Earth? 1,000 kilometers would be 1 million meters. So let's go ahead and do this. I've got the mass of the Earth and the radius of the Earth right here. So I'm going to plug those values into my equation. So I've got F, that's the force, that's the weight that I'm looking for. I've got G is 6.67 e negative 11, times M1, which that's going to be the mass of the Earth, that'll be 5.972 e24 kilograms, and then times the second mass, and that's going to be the mass of our person. That's going to be the 120 kilograms. And then divide all of that by the radius squared. So that radius squared is going to be 6.371 e6 squared. And just for context, that's 6.371 million meters. So this is in meters. So we can just plug all of that into our calculator and get our value. And when we punch those all in, we get a force of 1,170, and we'll round to 78 newtons. So that'd be the weight of this man. Now, what would be their weight 1,000 kilometers above the Earth? Well, if we wanted to do that, we would just take our radius here, and we're going to add 1 e6 meters, because that would be 1 million meters. So let's do that. Let's punch that in. We're going to use all the same values, 6.67 e negative 11. Let's use our parentheses the right way. 5.972 e24. And our 120 mass hasn't changed. Now we use 7.371 e6 because that's 6 plus 1 is 7. And then we square that. Now let's plug all of those numbers in and see what changes. And so now our mass, or our weight, goes down to 879.78, so let's round that to 880 newtons. And so we can see that our weight is going to change pretty significantly as our radius increases. And the inverse will be true as well. If we were to dig deep into the Earth, let's say we go let's go 1,000 meters closer to the center of the Earth. So let's change our radius. Let's just do that calculation quick to 5.371 e6. If we did that, our weight would increase. So if we decrease distance, then our force equals 1,657 newtons. So we get heavier. And so these numbers will change as a function of that radius. So now, how do we calculate G? Well, let's go ahead and do that here. Let's say this guy's force, let's say his weight is 1,178 newtons. And then he's going to have a mass and an acceleration due to gravity. This is just like F net equals ma, or when we said the force of gravity, the weight, was equal to mg. So when we take this value, we would replace m with 120. If we take this 1,178 divided by 120, what do we get? We get 9.8167. And so we would round that to 9.8 meters per second squared. And now we could do this more directly. We could take that universal law of gravitation. Let's do a different color here. Let's do some orange. We could take this And we could make this equal to our weight right off the bat, our mg. And so we could say it's equal to m2g. And if we did that, if we then divide both sides by m2, that was a terrible 2, divide both sides by m2, then our m2's all cancel out. And we're left with our weight equals our gravitational constant times the mass of the planet we're standing on divided by the radius of that planet squared. So if we're looking for any local field of gravity, I should actually change this F to a G. There we go. The local field of gravity for any planet is you're just going to need those two numbers, the mass of that planet and the radius of that planet. And those are usually pretty easy to find on Google. So let's plug these numbers in. Let's go 6.67 e negative 11. Let's make some room here. And then we've got, for our mass, 5.972 e24. And then divide that by the radius squared, which that radius is going to be, again, 6.371 e6 squared. If we put that all into our calculator, then we end up with 9.81365, which we could just round to 9.8. So we can see that we can calculate that acceleration due to gravity pretty easily. This isn't a very complex equation. And so we can figure this out for a variety of planets. And in your next assignment, you will. You'll be looking up the values for different planets, the masses and the radiuses, and you'll be determining that local field of gravity. So we should walk away with the ability to calculate using this equation. You should walk away knowing the value of g, and we should be able to figure out the local field of gravity. So let's go ahead and practice using this.